All right, so I've graduated, so now I'm gonna give a rundown of my physics thesis. This is just the presentation that I gave to my council. Um, yeah, I'm just gonna run through it for your sake, and also maybe I'll leave the full thesis in the description. Maybe I won't. I don't know. Anyway, so in general, the idea was to study a Foucault pendulum, and what I looked into was the period Coriolis force and apsidal precession. And then afterward, I compared some of the data that I have with the theory. This is just a picture of the pendulum. This is an old version, so this board down here is a prototype. It's the best functioning picture that I happen to have at the time. So specifically, what I'm going to talk about, honestly, who cares? It's table of contents. So Leon Foucault, after who it's named, was a French medical student, and then he didn't like blood, so he switched to physics, mostly because he was working with like microscopes of his like professors and whatever, and so because of that he got into optics, and then what he went into is this like daguerreotype, which is an early photography process, and so he made a lot of improvements there. And later in his life, he ended up working for the Journal of Debates, which was of the Academy of Science, which is like the most prestigious academic journal in France at the time. Uh, and then obviously he had his pendulum. He also did some other things like gyroscopes and whatever. He had like a speed of light measurement, but like what we remember him for is the pendulum. And an interesting thing is that the pendulum isn't actually originally done by him. It was done by this other Italian physicist, Vincenzo Viviani, like 200 years before. But that physicist was just trying to study pendulums in general. And so the Foucault pendulum, which has to do with the rotation of the Earth, this physicist did not figure that part out and was rather just annoyed by how it kept rotating rather than being in the same plane. The pendulum itself has to do with reference frames being, moving reference frames relative to each other. And the pendulum progression started with just a piece of vibrating steel and a rotating chuck, and then he made a 2-meter pendulum in his house. But because there was like the vibrations coming from outside, he got like a friend of his to put up an 11-meter pendulum in the Paris Observatory, and then because that was really popular, he got to put up a 67-meter long pendulum in the Pantheon of France, which I think is still the longest one. Supposedly there was a longer one in Russia, but they took it down like 20 years ago. And there's supposedly like going to be a longer one in Latvia, but I don't think it's built. So anyway, this picture is of the one in the Pantheon of France. So to understand, first we have to go over elliptic functions, and I just want to go over these two little definitions using differential equations. So you can define sine using this differential equation here, because if you take the derivative of sine, you get cosine, and you get cosine squared equals 1 minus sine squared. And that's just, move sine to the other side, you get sine squared plus cosine squared equals 1. That's the Pythagorean identity. So you can similarly do something else to define Sn, and this is the Jacobi sine function, and it just has this extra term here. It has to do, if you go to like the geometric side, it has to do with these two parameters, whereas sine has this parameter theta, which you may know as being like the angle around a circle. Elliptic functions have these two parameters. K is the ellipticity, or eccentricity, which is the ellipticity. Anyway, the point is that ovals, or ellipses, right? A circle has equal semi-major axes, right? If we're a unit circle, right? It's 1 to here, 1 to here. But if you double it, for example, right, you get an oval, right? If it's like 1 to here, 2 to here. So these axes are the B and A, and so you get this eccentricity depending on how eccentric the circle is, or the ellipse is. You'll notice if B and A are the same thing, right? If they're 1 and 1, or if they're like 2 and 2, then eccentricity is 0, which means it's just a circle. If K is 0, this term is 0, so you get just 1 minus y squared, and you get the return of this definition. So that's pretty cool. U is just the arc length along the ellipse, and it's done with this integral. And this right here is just a plot of like elliptic functions for different k values. You'll notice the closer it is to 0, the green is just closer to sine, and then the closer it is to 1, the less sine-like it gets. So what we're looking for, if we want the period of the pendulum, we're going to need the periods of these functions. And we can take this differential equation for sine, and we can separate it. And then if you integrate from 0 to 1, then you end up with pi over 2. Now what that means is you're integrating with respect to y from 0 to 1. And I have this little red area. And this integration from 0 to 1 is saying that when you integrate theta, you get whatever this distance is. This happens to be pi over 2, right? So it's not technically definitional, but it sort of is, because the way that you integrate this is you get arc sine, and so the arc sine of 1 to 0 is pi over 2. Anyway, if you multiply this by 4, right, you get 2 pi. So if you go from here to here, from here to here, from here to here, and then from here to here, the function repeats, right? It's just sine. So this integral times 4 is the period of sine. You can do a similar thing with Jacobi sine, where you take this, you separate it into this integral, and then you integrate from 0 to 1. So you get this integral plus this integral plus this integral plus this integral, and then the function repeats. Unfortunately, this is much harder to integrate, so you can really only approximate it. But kind of like how the other one was pseudo-defined as pi over 2, this is just defined as k, right? So the period of an elliptic function is 4k. Well, not any elliptic function, but Jacobi sine. Jacobi sine, the period is 4k, where k is this integral from 0 to 1. So now we can talk about the actual pendulum and how that period is found, which we solve through energy. Right? If you consider the pendulum swinging right here, right, at its highest point, well, first off, energy is a combination of the kinetic and potential energy, which is to say sort of the moving energy and then the energy in the field. So if you take the highest point, right, then it's not moving anymore, and all of its energy is in potential. And if you let that maximum angle be alpha, right, then you can plug that into here, into E, or for total energy. And then you can solve this equation for the change in theta, which is to say how this moves. And then if you fumble this a little bit with algebra, you end up with this equation, where omega naught squared is the driving, or the natural frequency of the pendulum. And so with this, you can make a substitution for phi, this right here. This isn't, like, this variable doesn't really have any physical meaning. It's just here to show the connection between, well, so what you'll notice, right, is if you put this substitution into the previous one, and then multiply by cosine squared phi, right, you end up with a form that is identical to this one, right? Since initially, this was done in terms of cosine, it's saying that cosine of theta is, the period of cosine theta is this, right? It's referring to this. So we find that the actual period of the pendulum is dependent on the maximum angle of the swing, because this isn't like a real variable. It doesn't super matter. And it also obviously depends on this. So you take this equation and then you can separate it just like before, yada yada, and then you end up with 4 times this integral is the period. So if you plug into this integral, this sine phi that we had earlier, then you end up with this substitution into this. And so from here, we can approximate with Newton's binomial expansion, and I just have the first 3 terms here. And then this is, I spoke with my contacts at the Chicago Museum of Science and Industry. By that I meant I emailed their customer support. Or not like customer support, but guest support, whatever. Anyway, so this is first order approximation, second order approximation, and third order approximation. And those approximations are, once again, these, right? Where k is, okay, well, I don't have it here, but k is this, right? Technically, you can do either one, where you have this is 1 minus y squared, or this is 1 minus k squared y squared, so k is this. You can convert it back into theta, and then it'll be 1 over... It's not that important. The point is, here I just have these approximations, and then I plug in the numbers for the stats of the Chicago Museum of Science and Industry. I don't have it with me right now, but it is a like 65-foot pendulum, something like that. So that goes into the length here, and it swings out, I think, a foot or something like that. You convert that to an angle, and then you take the inverse sine. You end up with this, or inverse sine over 2. So you can see here that, you know, these are very close together, and then these are identical, and that's because this term is to the power of negative 10, which means it's basically worthless for our purposes. And for there to be a 1% difference between the first and second order of approximation, it needs to swing up 23.1 degrees, which the pendulum we're using swings much, much lower, so we can confidently use this first order approximation, and it'll be fine. So now for the actual Foucault effect, we have to start talking about rotating reference frames, in which we consider these two frames, S0 and S, where S0, 0 sort of implying stillness, is the universe, and then S is the observer. So I have here just a little illustration, where at the beginning, the two frames are identical, and then this axis of rotation is here, that they're rotating about. And then over time, the S frame will rotate about this axis. And so you can imagine how an item like placed here, after rotating, even if it doesn't move, right, it would appear to have moved this way if you are rotating with this reference frame. So it appears to rotate. In reality, it doesn't. So what we're looking for is sort of how this motion works. So we can break the position down into its components, right? And since we're considering an object that is not moving right now, just the position is this, right? So basically, essentially what this is saying is the position in the universe frame is the same as the position in the rotating reference frame. So we need to take the derivative, but for that, we need to take the derivative of the vectors, since you'll end up doing a product rule here. Taking the derivative of these is easy because these are not changing. But these are changing, right? The directions themselves are changing. So we need to take a derivative of that. And what you find here is that for these like small changes, delta t, about an axis rotating with rate omega, you end up with this sort of limit. It's just the definition of a derivative. And then, you know, these cancel out, you end up with sine phi omega. And this, since we're considering a unit vector here, just rotating, this is actually the cross product, right? So you can imagine 1 times omega times sine phi, which is the angle between them. It's just a cross product. And so we can use that for our velocity, where again, like I said here, if you take the derivative of this side, you just get the velocity in the universe reference frame. But if you take the derivative in this frame, you end up with all of these terms, which recombine into just omega cross r. So we take the derivative again, and we can do a very similar thing, and we make a small approximation here, where this is the change in the rate of rotation, and technically, like, the Earth is slowing down, but it's not slowing down enough for it to matter, so we're just going to say that it's 0, and it's not going to, like, throw off any calculations. So anyway, you go through these, and you end up with this sort of equation for acceleration, and then we can multiply by mass to get Newton's second law, which is F equals ma for you non-physicists. So, you know, you go through that, and then you get this equation. Since we're looking for motion in the rotating reference frame, we just solve for this a here. So move stuff to the side, yada yada. So now we have these three terms. This term has to do with inertial forces in the universe reference frame, right? So someone pushing it, for example. This has to do with the Coriolis force, and you can see that it has to do with velocity, right? Velocity and the rate of rotation. And then this is the centrifugal force, which has to do with the position on the Earth. And if we didn't make the approximation here, we would have a third one, which is called the transverse force, but it doesn't matter here. So we're looking to study the Coriolis force, but we have these four forces on our pendulum, right? We're considering a free-swinging pendulum. We can deal with three of them at the same time. that being tension, gravity, and the centrifugal force. So the first thing that we're saying is that there is a force gravity and the force centrifugal, right? What you find if you take the cross products is that the centrifugal force is radially outward, and gravity is radially inward. So we can take the two and we can just combine them into like an effective force of gravity, rather than having force of gravity plus force of centrifugal. We can just combine them and say this is the effective force of gravity, and that's what we have here as mg. This should technically be Fg0, too late. Anyway, so this is mg, which is a combination of gravity and the centrifugal force, and what we're left with is the force of tension. So if we consider the forces in the z direction only, right, then we only have the tension, or the tension component in the z direction, which is going to be the cosine of the angle that it makes, plus whatever this is. And we're not accelerating here in any given, or not necessarily, but if you consider this sort of all of the forces in the z direction, then we get that Ft, which is the force of tension in the pendulum, times the cosine is equal to this gravity thing. But we're making an approximation here for small angles, which states that beta is small, which for small beta, right, cosine is like 0.1, 0.2, whatever. That's about 1. So we're saying that force of tension is just equal to this effective force of gravity. And so now we can solve for the other forces of tension in the other directions. And we can relate the forces to the lengths. So the force of tension in the x direction divided by the total force of tension is equal to sort of the displacement in the x direction over the length of the pendulum. And you could do the same thing for y. And then you just sort of rearrange this, and then this force of tension is this effective gravity. So now the other force that we need to consider is the Coriolis force, and it has this cross product, which we can work through it sort of basically. And the important thing is that this omega only has y and z components, right? And this is a sort of illustration explaining that, where this theta is the colatitude, or 90 minus the latitude. We're really only focusing on the x and y motion, so we're just going to ignore this component. It doesn't really matter for what we're doing. So if we go back to our equation of motion, right, we can now plug things in. This F, or inertial forces, we can combine. We have those tensions that we had earlier. And then this Coriolis force is this thing that we have from this cross product. So we can split this into x and y components, and we notice a small issue, being that it's a coupled differential equation, right? You have in the x direction, it's dependent on x and y, and then in the y direction, it's dependent on y and x. We can solve this by having a imaginary substitution, where we have this we have this complex variable n, where n is x plus iy. And then if we use that, then we can combine these two equations into just one equation. And then this one equation we can just solve normally like a differential equation, which we get this, and then we're going to make another small approximation here, saying that the rate of the natural frequency of the pendulum is much larger than the rate of the Earth's rotation, which is true. And so we're approximating that this term basically doesn't exist, so you end up with omega naught minus omega z, and then omega z is just the z component of rotation about the axis. Anyway, you end up with these two terms, and then to solve for these constants, we plug in starting conditions, which any would work, but let's just say that we're starting at the maximum amplitude from like no movement, right? So essentially we're pulling the pendulum back and then dropping it, and then that's what we're solving. Anyway, so you go through this solution, and then you end up with this final equation of motion. So it's saying that the motion of a pendulum under the influence of all of those forces I mentioned has to do with its amplitude, and then it sort of oscillates, and then this is saying that it'll turn in the plane, right? So if you just have a cosine, it'll do this kind of motion. But this makes it turn over time. And you're going to see that in a little bit. But first, one little minor point is that I looked into apsidal precession, which has to do with what happens if you're not swinging in a line, which ideally we want. If we don't, we can solve through these apses, which are the endpoints, or not the endpoints, I guess, but the extremes of the ellipse, right? So at these points, the z velocity is 0, right? Because they're hitting peaks. And using that, we can solve through to find that the additional precession because of this has to do with the area and the length of the pendulum, or the area of the ellipse and the length of the pendulum. So anyway, here's going into some of the data. These are just graphs showing what we expect to happen, right? So this is for 6 hours at a latitude of 90, which say at the North Pole. This, if you just think about it, right, if you have the Earth rotating under something that is just swinging back and forth, right, you would expect that in 24 hours, since the Earth goes around completely, in 6 hours, it would go around a fourth of the way. And so it's swinging back and forth, and then over 6 hours, it goes a fourth of the way. So, that's showing what we expect. Unfortunately, because this is like so many movements, it's crowded and getting bad. So I switched to a theoretical Earth, which spins 3,600 times faster. And the result of that is that 6 hours can be modeled by 6 seconds, so we get a much cleaner graph. This is showing the exact same thing as this, but it's got less lines. And you can see how that makes sense. So if we scoot it down to Chicago, which is at a latitude of 42, this is a plot of supposed 36 hours. In reality, it's 36 seconds on this imaginary Earth. But what it shows is what we expect, right? It starts right here, and then, it curves around, and you see 2 spikes everywhere. And the meaning of that is that it has gone around 1 full time. Because here, right, this is 90 degrees. If it went 180 degrees, then it would be complete, right? It would complete the circle because it's moving back and forth. So to go 360 degrees, we need to double over everything. So this is what we're seeing here. This is some data that I took over the summer, not this summer, last summer. This is originally a 100-ish hour run. This is just taking the first 36 for showing what's happening. Each of these is finding a different sensor, right? This is the setup that we have, where the pendulum swings over these, there's little magnets on the bottom of it, and then when the pendulum swings over them, they give a response. And so we can track that over time. This is actually taking out 90% of the data points. It's a lot uglier and unreadable, so I made some changes. So we're looking at all of these sensors here. There's 9 of them, which we're using to track. And we started it over sensor 2. So what we expect, based on this, is that in 36 hours, we'll be back at sensor 2. Right? So we go here, and then we go here. This is where we expect this 36-hour line to be, but it's not. Which means that we're going too fast. Additionally, what you can see is that we're not uniform at all, basically. The gaps between these two are much smaller than the gaps between these two, and that's staying consistent. What we find is that all of the sensors are consistent with each other, but they're all running fast. What we expect is 10.1 about degrees per hour, and what we're seeing is 11.5. And so obviously the question is, what's causing that? So as I mentioned, apsidal precession could be really, really bad. This right here is a graph that's sort of hard to see, but it's showing 100 cycles for an ellipse that it has apses that are 1 to 100, which, if you run through the calculation, you find that they'll do about 0.97 degrees of precession over the course of 5 minutes. Now, the Foucault effect, which we're trying to study, that, over 5 minutes, would change the plane of rotation by 0.84 degrees, which means if they're aligned, then we would have double the rate. If they're not aligned, then it would appear that our pendulum's going backwards. But our pendulum's going forwards, and it's off by just a little tiny amount, realistically. So this is likely not the source of error, especially because we're taking measures to prevent it. This is sort of the underside right here is where you can see the pin vise down there. Right here, this way, is where the wire from the pendulum sits, and then this is like a metal ring, right? The wire hits the metal ring, and then the idea for that is that when it hits the metal ring, all of the tangential velocity is stopped, so it can't possibly have elliptical rotations. It only has to swing in a plane. There is a downside. There's the downside that once the pendulum wire hits the metal, we have like a two-stage pendulum. Rather than the pendulum hitting the wire and then staying the way it is, now, can I draw? Aha. Okay. So the pendulum swings, right, and then it goes this way, and we have the ring, right? So it hits this ring. In an ideal universe, it would just go straight back, and then perfect, we're all happy. But if it's not ideal, right, then it keeps going this way, right? Now, this length is different from this length, which means we now have a two-stage pendulum. And even worse, it swings back this way, it hits this way, and now we have a pendulum that starts at two different places. So this might cause issues, but the point is that we're not getting this apsidal precession, which we're trying to avoid in the first place. Likely, what I think is the issue, is the magnet kind of sucked. That's because I made the magnet myself. I wound about 5,000 feet of wire. It took me a couple hours. And so the result of that is that it's probably not even, which means it'll probably not pull the way that we expect it to everywhere. And I guess I didn't cover what the pendulum actually looks like and how it works. But essentially what we have is, okay, time for the pen again. Essentially what we have is this setup here, which is this. This setup is here. And then there's a metal cylinder on the wire. There's a bob down here. There's a metal cylinder on the wire. Once these lasers are blocked, right, this goes this way, this goes this way. Once both of these lasers are blocked, it means that the pendulum is swinging through the center. When it swings through the center, we turn on the magnet here, which means whichever direction it's going, it'll pull the wire a little bit this way. So instead of the pendulum dying over time, it gets pulled every time it goes through the center. And so that's how it's driving it. And because of that, it hits this ring, and then ideally it doesn't become an elliptical rotation. But because it's not a uniform magnet, it'll pull differently in different places, which could potentially cause these sort of gaps. I think that's what's the issue. I haven't looked into it. This was not something that I had the time for. I ran out. Anyway, so the conclusion that I sort of got to is that the period of the pendulum, we could just use a first order approximation. It doesn't matter. For a pendulum swinging in a plane, the plane of the oscillation, which we're trying to study from the Coriolis force being the Foucault effect, it'll rotate depending on the co-latitude, which is, it's depending on the position of the pendulum on Earth. And then for the apsidal precession, it could destroy the pendulum, but it's probably not. On the experimental side, which is sort of what I did over the summer, we could track the pendulum with a reasonable amount of sensors and pretty accurately. Of course, if we had like 35 sensors, it would be better than 9. But, at what point do you stop? And 9 is good enough to show us what issues we're having. So that's good. And then the important thing is that the pendulum moves somewhat as we expect it to, but there's some source of error. When I originally started working on it, it was barely driving, and then when it did, it was like completely random which direction it would go. So there were some serious issues there. I went to working on that, I tweaked a bunch of stuff. Anyway, I have these like little summary slides in case my counsel wanted to ask questions. But this part is something that I covered in my thesis. You'll notice the apsidal precession was short. It was by far the longest derivation. And this is just like a quick breakdown. I might as well give it to you. It has to do with, since what I mentioned was we're using the z position, or to say the height of the pendulum, to solve all of the stuff. And we can use this equation, which is pretty obvious. It's just that the radial distance, I wish I had the, okay, I can just draw it. If you have the ellipse, right, the radial distance along any of these points is just the length squared minus the height. And you can imagine that sort of just on a sphere, right? It's just the distance. It's just a distance equation. There's nothing to it. This is just the derivative, and then we solve in terms of this change in r. And then this is angular momentum. In this case, it's just defined as this because we're only considering it rotating sort of around this way and then no other motion. And we can solve it for this just in terms of the changing in phi, which is the angle this way. This is in cylindrical coordinates. So r, phi, and then this way upwards would be z. Anyway, from that, we can start again with energy, and then yada yada, we rearrange it, and then we can plug in the equations we found on the last part. And then once again, we solve for this z dot squared, or the velocity of z. And you'll remember that I mentioned we're looking for the points where z dot is 0. That's kind of hard to get, and especially when we factor this into this. But just using some algebra, we know that since this is cubic, right, because you get z squared times z, it'll be to the third power, we know that there is a function that we can solve with these z1, z2, z3. And so we can solve this, or we can take this theoretical equation and this actual equation, and then we can just match them to get the different variables. And then what we're looking for is the change in the angle of rotation this way, right? So we're looking for this, and we have this definition here. Now this dot in physics, and I guess in math, but traditionally in physics, is just saying the derivative with respect to time. So we can chain rule that to be with respect to this z position, which we, in theory, know. So this we have from before, and then this is the sort of just squaring this equation, and you can kind of see maybe where this is going to see more elliptic functions. Anyway, yada yada, make some substitutions, and then we end up with these integrals. AA here is the change in apsidal angle. This is used as a small approximation here, where it's like we're making the assumption that the pendulum is swinging toward the bottom. So this is just minus L plus Z. Or no. Other way. Anyway, the point is, this is just a small approximation. We can convert it back later, which we actually do here. Because you'll notice it combines into this square. L is the length of the pendulum. S is the sum of the square terms, or the sum of the square root terms. Which if we go back here, right? So since eventually we need to unsquare this, we need to take the square root to get rid of this. Then we end up with these. And then you end up with sum terms and then difference terms. And then D is the difference terms. And we're looking for from Z1 to Z2, which you can sort of imagine it's like a chip if it's swinging in an ellipse. And then Z1 is one of these solutions, Z2 is one of these solutions. And then you can see kind of there's a fourth, there's a fourth, there's a fourth, there's a fourth. Yippee, elliptic integrals. We can solve these, yada yada, we'll get this solution, and then we can make some more algebraic simplifications. We end up with this, some difference, and then if you use this pi, then you end up with the area of the ellipse, divide by 2, not divide by 2, but it's saying that the change in the angle is equal to pi over 2 plus this 3 times the area, wow, my handwriting's bad, over 16L squared, right? But since this is a fourth, we multiply by 4, you end up with the change in angle, the change in angle is 2 pi which is what we expect. After one rotation, it goes by around 2 pi, plus this little extra 3a over 4l squared. So that's the upside precession. Oh, good. I had that slide already. Anyway, yeah, so that's the extra precession. Yippee. Okay, that's my thesis. Wahoo. Hope that was fun or interesting or helpful. I don't know, whatever.